State the law of conservation of momentum. You must say it's linear momentum. You must say it's in a closed system. I mean, we all know conservation means it stays constant, so yeah, that's in there. But it's got to be linear and it's got to be in a closed system. Calculate the speed of car B immediately before it collided with car A. So you're going to have to say momentum before is equal to momentum after. And then you're going to need to say that you've got 1,500 as a mass of car A multiplied by 20. You don't know car B, which is 1,000 multiplied by I don't know what, is equal to the combined mass and a combined velocity of 6. Now you'll notice that my 20 is to the right and that my 6 is to the right, so I've made them both positive. When I work out U, I get a positive 15. They want speed. Speed is not a velocity. It does not require a direction. So you do not put a direction in. I didn't subtract a mark, but I could have, because you don't understand what speed is if you stuck a direction in there. Right, the next one. Use suitable calculations to determine whether or not the collision was elastic. The fact that they combined with each other means that it probably isn't elastic, but it does say show with suitable calculations. And what is an elastic collision? You need to look at the kinetic energy before and the kinetic energy after. You cannot say that they are equal. You need to say kinetic energy before is equal to a half mv squared, which is equal to a half 1,500 plus 20 squared plus, times 20 squared plus a half of 1,000 times by 15 squared. That is the total kinetic energy before, and it comes out to be 412,500 joules. What is the kinetic energy after the collision? It's equal to a half of mv squared, which is equal to a half of 2,500 multiplied by 6 squared, and that is only 45,000 joules. Well, those two are obviously not equal to each other, and therefore it is an inelastic collision. Then it says calculate the magnitude of the driving force on car A before the collision if the power used is 38,000 watts. We know that power is equal to force times velocity, and so the power is 38,000 watts because we need to go into watts to do this calculation. We're looking for a force, and we've got velocity is a constant 20 meters per second, and therefore this force comes out to be 19,000 newtons. Again, it is magnitude of force, so we do not wish to have a direction. What is impulse? It is change in momentum, or the product of the net force versus and contact time. Which car, if any, experiences a greater magnitude of impulse during the collision? It's neither. They are exactly the same during the collision, and let me tell you why. Just find ourselves a little bit of space. What you've got is you've got change in momentum is equal to force times time. Since from Newton's third law, you know that the force on the one object is equal to the force on the other. So the two forces are equal. And you do know that they are in collision for the same amount of time. So the time is equal. And therefore, if the forces are equal and the time is equal, the change in momentum must be equal as well. So neither of them has a greater magnitude of impulse. We've got two different balls. Both their masses are in grams. You do need to convert both of those into kilograms before you do anything else. And they tell you a direction and a velocity for each of those. And then they say that the impulse is 1,5 to the left. So you're going to go change in momentum is equal to mv minus mu. 1,5, I'm going to make left positive and right negative. And sometimes I'm as explicit as writing that on the side so that I don't stuff it up. So I'm going to say 0,25, and my velocity is v minus, and now to the right, which is here, I'm going to say minus 4. And when I solve for that, my V turns out to be a positive answer of 2 meters per second, and therefore it is to the left. Then we've got calculate the magnitude and direction of the velocity of ball B immediately after the collision. So momentum before is equal to momentum after, and that is 0,254. And this time, I don't know why I did it, but I made my right positive. I suppose we should stay with the same convention. So it's to the right is negative, so I'll put a -4 in there, plus 0,6 to the left is positive, is equal to 0,25, change that, plus 0,3. And when I re-evaluate all of that, I come out with a positive answer again, and it's 1 meter per second to the left. This was a very standard question, and it came in at level 2. There was nothing weird in it at all. This is a little bit tricky because of this negative, but you've got to start paying attention to that and knowing that that's going to happen every time with an impulse. Right, we've got a small block, and it's up here, and it's going to go along and up to there. We've obviously got changes in heights over there. What is the average speed of the block? And average speed is as simple as distance over time. So it's 8,1 meters over a time of 3 seconds, and it's 2,7 meters per second. It's an average speed. We're not worried about acceleration, so we're not using equations of motion at all. Also, we don't want to use equations of motion because we're changing. It's not rectilinear motion at all. So use the principle of conservation of mechanical energy to calculate the speed of the block as it reaches D on the track. So we are going to need to consider both kinetic and potential energy in this as we consider the two together. So it's going to be at point A and at point D. The kinetic energy plus the potential energy is equal to the kinetic energy plus the potential energy, and that is going to be, there's no kinetic energy, it's standing still over here, so it's 0 plus mgh 0,4, 9,8, and the height is 0,8 is equal to a half 0,4. I don't know the velocity, plus 0,4, 9,8, 0,3, and V turns out to be 3,13 meters per second. And again, they asked me for speed, so we do not want a direction. State the work energy. Sorry, I didn't talk through state the principle of conservation of mechanical energy. You need to say that mechanical energy is kinetic plus potential energy, and it remains constant in a closed system. Stating the work energy theorem, the work done by a net force on an object is equal to the change in kinetic energy of that object. Calculate the magnitude of the frictional force acting on the block between position D and E, and the distance is 3 meters. So the first thing I'm going to do is I'm going to say my original kinetic energy, I've just worked out a speed over here, at point D is going to be equal to a half mv squared. That is going to be a half 0,4, 3,13 squared, and that's 1,96 joules. All of that energy is going to be lost by the time I get there, because the change in kinetic energy, if you think about it, this object is stationary over there, is going to be equal to 1,96 minus 0, which is going to be equal to 1,96 joules of work that is done. And work that is done is equal to, work done, it's on your information sheet, is force times distance. So I have not got a force. I have got a distance though. I have got it was 3 meters, eh? Yeah. So it's 3 meters. So force is going to be equal to 0,65 newtons. What is the only force acting on this object between here and here? Well, it was going zoom, zoom, it's got some speed, and there's only one thing slowing it down, and that is the only force is friction. So that is the frictional force that is acting against it. The net force is 0,65 newtons against the motion. But again, they only ask for the magnitude, so I don't have to say against the motion. We find that the angle is 36 degrees over here of a box, and it accelerates from rest down a rough slope of a certain length. because it's a rough slope, I cannot just take the kinetic, at least the potential energy, and say that that is, and work out the kinetic energy at the bottom. Because if there was a frictionless slope, going down there would be exactly the same as falling down there. But there's friction involved, so you're going to have to either compensate for the friction, of which they tell you very little, in fact nothing. So you have to actually just take this as a straight line and use equations of motion. What is the velocity of that box? V squared is equal to u squared plus 2as. So that's equal to, it starts at 0. We're told its acceleration, and we know how long it does that for, and we get 12,3 meters per second. Don't forget to square root. Again, magnitude of velocity, no direction over there. Then state Newton's second law. An unbalanced force acts on an object, the object accelerates. The acceleration is directly proportional to the unbalanced force and inversely proportional to the mass of the object. Thank you to most of you for having learnt your laws. You did fairly well on that. Calculate the magnitude of the net force acting on the box as it moves down the slope. So we're now saying force net is equal to mass times acceleration. I've got a 12 kilogram block, and it has a 4,2 meter per second squared acceleration, and it's as simple as that. And then calculate the magnitude of the frictional force acting on the block. Well, I know that I should have a total force of... Right, now I'm going to consider that I have got a weight acting... Oh, make this a little bit smaller and get some space. I've got a weight acting down over there. That weight can be broken down into a component down the slope and a component perpendicular to the slope like that. I am interested in the part of that force that is going down the slope over there, and I can say that the force parallel is equal to 12 sine 36. How do I know that? I'm going to put that in there. I've got another... There's my 36 degrees inside there. That's my parallel component. It's opposite. So the parallel component is opposite to the 36. So I'm going to use sine. So it's sine 36 degrees is equal to 69,12 newtons down the slope. And we do know that the net force is equal to the applied force, or the big force, minus the small force. So the big force is 69,12. The small force would be friction. But the net force is 50,4. And therefore, I land up with my frictional force being equal to 18,72 newtons.